We've all imagined it, going back in time to fix a mistake, save someone we lost, or witness a great moment in history. But time travel isn't just a fantasy, it's a puzzle. And at the center of that puzzle lies a dangerous contradiction, the paradox. If we travel to the past and change it, how can the future we came from still exist? This idea creates a logical mess. For example, take the classic grandfather paradox. You go back in time and prevent your grandfather from meeting your grandmother. That means your parent is never born, so you're never born. But if you never existed, who went back to prevent it all? This creates a loop that has no consistent answer. It violates causality, the principle that causes must come before their effects. Another version is the bootstrap paradox. Imagine you hand a young Beethoven a symphony from the future. He copies it down and becomes famous. But where did the symphony originate? Not from Beethoven, not from you, it seems to have no beginning. It just exists in a loop. This kind of paradox doesn't break time, but it breaks logic. It creates a world where things can appear from nowhere, and that's deeply unsettling to physics. So if time travel causes contradictions, can it be real? Surprisingly, the laws of physics don't shut the door completely. In fact, Einstein's general relativity allows for something called closed time-like curves, paths in spacetime that loop back on themselves. These loops are theoretically possible if space is bent just right, such as by a rapidly spinning black hole or a traversable wormhole. In such a loop, you could, in principle, arrive at a moment before you left. But once again, the paradoxes return. If a particle, or a person, interacts with their past self, could they change something that stops the original journey from happening? That's where physicist Igor Novikov offered a bold idea: what if the universe simply doesn't allow paradoxes? Novikov's self-consistency principle suggests that any event occurring on a closed time-like curve must be consistent with its own history. In other words, you can go back in time, but anything you do was always part of the past to begin with. You can't change history, you're fulfilling it. This might sound like a cheat, but it fits surprisingly well with what we know from quantum mechanics. In 2020, physicists simulated a time travel scenario using a quantum computer. They allowed a qubit, essentially a tiny unit of quantum information, to interact with a version of itself from the past. When a paradox started to form, the system naturally adjusted. The probabilities of paradoxical events dropped to zero. The outcome was always one where the timeline stayed consistent. So instead of forbidding time travel, nature seems to rewrite probabilities to protect causality. This means the past can be visited, but never altered in a way that causes a contradiction. Of course, this idea brings up another concern: what about free will? If the timeline has to stay consistent, doesn't that mean your choices are locked in? Not necessarily. It just means that whatever choices you make have already been accounted for. Think of it like playing chess in reverse. Every move you make fits the final position, but you still had options within the structure of the game. Your freedom exists, but it's constrained by logic. Still, not all physicists agree with the self-consistency principle. Another explanation comes from quantum theory, the many worlds interpretation. In this view, every possible outcome of every event actually occurs in a separate universe. So if you go back in time and change something, you don't rewrite your original timeline, you create a new one. You still came from a universe where your grandfather lived, but now you've branched into a new one where he didn't. This sidesteps the paradox entirely. There's no contradiction because every version of events exists in its own world. The only downside? There's no going back. You've left your original universe forever. Both models, the self-consistent loop and the many worlds branch, are internally logical. They just offer different pictures of reality. One says the timeline is fixed and paradoxes are impossible. The other says timelines can split, creating infinite versions of history. But can we actually build a time machine? That's where the science hits its limits. Wormholes might offer a path, as suggested by Kip Thorne and others. If you move one end of a wormhole fast enough, time dilation, predicted by relativity, would make time flow differently at each end. Entering the slower end could let you exit into the past, relative to the other. However, keeping a wormhole open requires exotic matter with negative energy, something we've never been able to produce in the amounts needed. And while time dilation is real, we've observed it with fast-moving satellites, it only lets us travel forward in time, not back. Black holes offer another form of extreme time manipulation, but they trap anything that gets too close. No escape, no return, and no second chances. So have we solved the time travel paradox? In theory, yes. Physics suggests that if time travel is possible, paradoxes won't happen. Quantum systems adjust their behavior to stay logically consistent. And in the multiverse view, every outcome gets its own timeline, avoiding contradictions altogether. But in practice, time travel to the past remains a distant dream. For now, the arrow of time moves forward. We can imagine it, simulate it, and even glimpse its edges, but we can't bend it just yet. Still, the mere fact that we're seriously asking these questions tells us something profound. Time, as we experience it, may not be the whole story. And one day, understanding its true nature could rewrite everything we know, not just about the universe, but about ourselves.